In this video, we'll be covering related rates around a triangle. Now, in this particular question, it is a very, very common question in all calculus classes. A ladder 10 feet long is leaning against a warehouse when the top of the ladder begins to slide down the wall. So let me draw that image, or the concept of what's happening. So here's the wall, here's the ground. We have a ladder that's leaning against that warehouse. Again, this ladder is 10 feet long. Notice in this case, I'm going to go ahead and make a note about this right off the bat, is that this ladder is 10 feet long and this ladder length isn't changing at all. Okay, so this right here isn't changing. What is changing is that it begins to slide down the wall. So I'm going to go ahead and draw an arrow down this way, which means that there's going to be an arrow that's pointing out this way. So this point is getting further and further away from the wall. This one is coming down closer and closer to the ground. So the question is, by the time the base of the ladder is 8 feet from the building. So let's go ahead and label some variables here. Notice there's no variables labeled on this picture, but I think labeling this picture first will help us understand where this equation came from. So I'm going to call this distance right here from here to here x. I'm going to call the distance from here to here y. So the distance that the foot of the ladder is away from the wall is x. The distance that the top of the ladder touches the wall is y. So let me read this one more time. By the time the base of the ladder is 8 feet from the building. Okay, so that means that when the distance x is 8 feet, when the base of the ladder is 8 feet from the wall, the top of the ladder is moving at a rate of 3 feet per minute. Okay, so that means dy dt is changing at a rate of 3 feet per minute. Now let's be very careful with this. We already said that this ladder is moving downwards. And by the concepts of the previous examples, we should always identify that if a length is changing in a decreasing motion, that means that dy dt in this case should be negative. Again, this one is decreasing in length each time. This ladder is moving down, so the length is going to be here, then it's going to be here, then it's going to be here, and this distance here, or this distance here, or this distance here is getting smaller each time. Whereas an x is actually getting larger because this is being pushed out, so again, it's going to move here, and here, and here. So this is going to get larger each time. So dy dt is moving at a rate of 3 feet per minute, but it's moving at a negative 3 feet per minute when we consider it moving down the wall. That distance of y is shrinking. So the question is, how fast is the base of the ladder moving away from the warehouse? So the question that we want to answer is, what is dx dt? That's what we're really looking for. Now, the question here then revolves around what equation relates this, this, and this. Those three sides. Well, if we're very careful, you'll notice that this is a 90-degree angle. And these three sides will be related by the Pythagorean theorem, which is right here, again given in this problem. So I know x squared plus y squared equals to z squared in this case, where this is my x, this is my y, this is my z. Let's go ahead and fill in this table for the rest of the information I don't have. So let's see here. I know z is 10. I didn't identify what dz dt was. Let's go ahead and see if we can identify dz dt. Now, what is the change in the length of the ladder over time? Now again, we kind of said this earlier, the ladder is 10 feet long, unless this is one of those special ladders that extend, which we're not going to want it to extend when it's on the building. We're going to assume that it's not changing in length at all. So again, it's going to be like this is moving in this direction, just like this, as I move these two pieces. dz dt doesn't, z doesn't change, so dz dt would be 0. And the last piece that I notice I don't have, I have x, I have z, I don't have a y value. Well, I don't know that I need that y value yet, so we're not going to go ahead and find it, but I found all the other information that seems logical and very quick for me to find. After we find all the information we can considerably find, again, could I find y? The answer is always yes. If I'm missing a value somewhere in here that's not a rate, I can go ahead and plug everything I do have into this formula and solve for that missing piece. But I'm going to go ahead and hold off on that just in case if I don't need to do that. What I'm going to do is I'm going to start by simply taking the derivative of both sides of this equation in respect to t. So I now have this set up, and I need to take this derivative of both of these terms. Now keep in mind, be very careful, we're taking the derivative in respect to t of variables x, y, and z. So the derivative of x squared, the derivative of anything squared, is 2 times that anything to the power of 1. Then your next step your next step is to take the derivative of the interior piece. So the derivative of x in respect to t is dx dt. Then I'm going to go ahead and do the same thing with y. The derivative of y squared in respect to t is plus, that's the plus sign carrying down, 2y, and then dy dt. Again, every time you take the derivative of a variable that's not the variable we're taking the derivative in respect to, we got to tack in that extra dy dt piece. So then in this case right here on the last side, we have 2 times z dz dt. Okay, so if I look through all this information, the goal again is to find dx dt, which I have right here. This is what I'm looking for. I'm going to go and throw that in parentheses. I have x. I don't have y. So it does look like in this particular type of problem, we do need to find out what y is before we do any other work. dy dt I've been given. Z I've been given. dz dt is 0. That wasn't given, but we again logicked our way that the ladder's not going to change in length. So I can plug all the information in, but I still need y. So I'm going to go back up to the original equation. If I'm missing a piece that is a constant, or I shouldn't say constant, I should say if I'm missing a piece that is a single variable, not a rate variable, then I can go ahead and plug all the information I have in one more time. So in here, I have 8 squared plus y I'm missing, and z we said was 10. So 10 squared is 100, 8 squared is 64, and I can go ahead and subtract 64 from both sides and get myself that y squared is equal to a 36, which tells me that y is equal to plus or minus 6. But in this particular problem, y, this length, again, is a positive value. The length is positive. dy dt, the rate at which this length is changing, is negative. So y will start at its maximum value of 6, and it will decrease, hopefully to a minimum value of eventually 0. But now that I have what this is at the time when x is 8, z is 10, and dy dt is negative 3 feet per minute, I can plug all this information in and solve for dx dt. Doing so, I'm going to replace x with my 8. dx dt is what we're looking for, so I'm going to leave that unchanged. Plus, I have 2 times my y is 6. dy dt is up here at negative 3, and again, remember it's negative because the length of that distance is decreasing. Z is going to be 10. And dz dt is 0. So this side here happens to be equal to 0. Then over here I'm going to have 16 dx dt minus, looks like a minus, 3 times 2 is 6 times 6 is 36. And then solving this for dx dt, I'm going to go ahead and add the 36. I'm going to divide by 16, and dx dt is equal to 36 over 16. Again, we can simplify this a little bit to be 18 over, looks like 8, and simplify that again to give me, looks like 9 over 4. So this is our final number. What's the final answer? Well, we have to remember, look back at the information given in the problem that we started with. I'm looking for a dx dt. dx, x is in terms of feet. Again, you'll notice that right here. So x is 8 feet. That means that this rate of change should be 9/4 feet in respect to time. Well, what's time in this particular problem? Again, if you look back, you'll notice that it's 3 feet per minute for the ladder moving down at that rate. You'll notice that this one here is feet per minute. Again, everything in this problem is in terms of feet, and the rate of time is minutes. So this final answer will be 9/4 feet per minute. Now, I'm hoping that this is the right answer. How can we make sure that that makes sense? Well, let's look back at this problem. And dx dt is this value down here. So I'm going to go ahead and write dx dt down here. And over here, this is my dy dt. Let's talk about these values one more time. dy dt we said was a negative value because it is decreasing the length of this side. dx dt should be a positive value because it's increasing the length of this side. And you'll notice dx dt in this problem is 9/4, or again, approximately 2 and some change feet per minute. A positive value, which makes this concept make sense. So therefore, we would argue that this is the correct answer we're looking for.